So dear student, and then the last topic we are complete that the design of op-amp. Now we are start that how to compensate an op-amp. So what is meant by compensation? Basically that whenever the op-amp we are used, basically the op-amp are used in negative feedback. Why is negative feedback? Because we know that there are two types of feedback. Either it will be positive feedback or it will be negative feedback. So why we use that the negative feedback? Because we use the negative feedback to get that the relatively high gain. We get that the high gain, basically that to reduce the noise and to get that the high gain, we are use that negative feedback. So here, whatever that the circuit are used in here, that is basically a single loop negative feedback system. Why it is called single loop? Because here, this is the only one loop it will be attached. And why it will be negative loop? Because this is that the summation point. So whenever we can apply that input voltage and whenever this is AS, it is called that the op-amp, and this is called that the feedback amplifier, and this is called internal amplifier. So whenever the output, the input of internal amplifier or the input of A, it should be that the negative of that Fs minus of Vns. So this one, it is called that the negative feedback, because whatever the feedback system, that feedback through that the feedback network path, that should be is connected to that the negative symbol. So that's why it is called that the negative feedback. Now what is that the loop gain of negative feedback? So we can measure that the loop gain means Ls. Why we can design that S? Because here we are design in that frequency domain analysis. We can't design that the time domain analysis. So that's why whenever all that the system we are design all this in that the frequency domain analysis. So here whenever we are write down any of that the items, either it will be gain or it will be input voltage or it will be output voltage, we can define in that the frequency domain. So A symbol is means that is the frequency domain. Now what is that the loop gain? Loop gain means that will be AS multiply of Fs. That is called that the loop gain, and loop gain is negative because that loop is that the negative feedback loop. So that's why the loop gain is minus AS multiply of Fs. Now, if we consider one case, let us example that the forward gain from V into V out is unity. Forward gain means that gain of A. Let's consider that A is unity and the DC gain, that is open loop gain, if there will be no feedback, then the open loop gain is A. So if we consider the open loop gain of DC A0 is between 1000 to 2000 and the feedback factor or the feedback gain F is equal to 1, then the forward gain is varies from 0.999 to 0.9995. So for any high gain loop, we are required that the transfer function, that means the output voltage by of input voltage, the forward transfer function is controlled by the feedback network. So if feedback network is not controlled, if the forward transfer function is not very high, then there will be chances for the noise creation. There will be some chances it will be there. So we require that the forward transfer function. Why it will be forward? Because the transfer function is output by input. Now why is reverse transfer function? Reverse transfer function means input by of output. But here we consider the forward transfer function. That means output voltage by of input voltage. Op-amp, why it will be voltage? Because op-amp basically gives that whatever that the voltage we are applied at the input, we are get that the output as enough voltage. There will be input and output, we can apply any type of power or current instead of voltage. So here whatever the op-amp we are designed, the output and input should be of voltage. So that's why the transfer function also output voltage by input voltage. So this type of principle is applied in that the op-amp. Now we are go to the small signal dynamics of two-stage op-amp. So, in the small signal analysis of two-stage op-amp, already you know that what are the small signal analysis. Now, here we consider, already we are told that we are consider that the frequency domain analysis. So, in that frequency domain analysis, what we design in here, that will be, we have to know that the Bode plot, we have to done that the small signal analysis by using of that the Bode plot, and by using of that the Bode plot, we are measure that what is that the phase margin of two-stage op-amp. Now here we are consider one omega 0. So what is that omega 0? Omega 0 is nothing but the angular frequency of that the voltage, or of the time period of that the voltage. Now if the primary importance of that the signal feeding to that the input of that the op-amp, that means that the amplitude and phase that does not continue to regenerate itself around the loop. What do you mean by regenerate itself? Regenerate itself means it is nothing but an amplifier. It going to be an oscillator. So we not design here any type of oscillator. We are design that op-amp. So for the design of op-amp, we not go for regenerate the signal in the loop. So if that the output of that, the result will be either clumping of that the output of that the amplifier, one of the supply potential, that means the regeneration at DC, and oscillation, that regeneration of some frequency other than DC. The requirement of avoiding this situation can be sufficiently stated by that the following equation. So what is that following equation? We can define that the following equation. So previously we see that the loop gain is AS into FS, but here we consider the S is nothing but J into omega naught. So we are consider not that the negative or positive loop gain. We are consider the unity loop gain, or magnitude of that the loop gain, or modulus of that the loop gain. So that's why we not consider anything negative in here. We consider the mod of A multiply of F, that is equal to L of j omega is equal to less than 1. If this condition is satisfied, then only it does not continue to regenerate itself around the loop. Now, how to define that the omega 0 angular frequency? The omega 0 is defined by this equation, and that will be that the angle of the loop gain is equal to 0. If angle of that the loop gain is equal to 0 and that modulus of that the loop gain is less than 1, so this one is basically that equation. First equation is basically for that amplitude equation, and second equation basically that phase equation. So if these two equations are satisfied, then only we can tell that the amplitude and phase does not regenerate itself around the loop. Now how to design that? The another convenient way, that by this equation, because here we are considered the omega 0 is an degree. So the another way, if we convert that the degree equation to decibel, everyone knows that how to convert the degree to decibel. So if we again convert from degree to decibel, so this is that the equation, and for that equation it should be angle of that the loop gain, which is converted to dB, it should be greater than equal to 0 degree, and where omega 0 dB is defined by that loop gain is equal to 1, or the modulus of that the loop gain is equal to 1. If all these conditions are satisfied, then the feedback system is said to be stable, or it is that sustained oscillation cannot occur. Now that the fourth equation, whatever the equations we can consider, that the phase margin, from that the phase margin, if we equation that we are used at the Bode diagrams, that this one is that Bode diagram. The first one, is that amplitude diagram, and second one is that the phase diagram or that angular diagram. So here that you see that there will be that two poles are there, because whenever we are designed at the two-stage op-amp, so obviously there will be two poles will be there. So this is that the first pole, this is the second pole, and obviously according to Bode plot, if we see that is 20 dB per decade, it should be continue after that the first pole, and from that after second pole that the decade should be minus 40 dB. And obviously if we see that the angular frequency, whenever the magnitude plot is touches in that the zero, that phase plot is not touching zero. So from that, whenever it touch at zero at pole 2, whatever that the phase it will be there, this is called that the phase margin. So this phase margin we are defined by this formula, that is phi m is equal to argument or the tan inverse of loop gain, that is converted to that the dB. And why is required for that the phase margin is required, that the good stability. That importance of good stability is obtained with adequate phase margin is best understood by considering the response of closed loop system in time domain. So this is that the response of second order system. This is that the slew rate V out by of AV naught, that is the output voltage with respect to that the DC gain, and this will be that the angular frequency with respect to time. This should be in radians, and this is all are, there will be no unit of that the magnitude. So if we see that there will be some of that the response, and after some time it is meet at 1. So these 70 degree, 60 degree, 65, 40, 45, these all are the phase margin of that system. So if we consider that, we see that for that the 60 degree of phase margin, for this 60 degree of phase margin, that the plot is nearly equal to 1. So we are considered that the thing, whenever is that, the thing is that it is basically that phase margin of at least is required 60 degree for that the good stability. Now for consider of that the second order, that the op-amp of second order, two-stage op-amp small signal analysis model. So this is that the first stage, and this one is that the second stage. So GM1 means first stage, transconductance, and GM2 means overall second stage transconductance. C1 and R1 is that the first stage overall capacitance, second stage overall resistance, second stage overall capacitance, second stage overall resistance. V in is that the input voltage, V out is output voltage, and V1 is that the voltage which is transferred from first stage to second stage. So for this two-stage amplifier, we are considered two poles. One is that the pole 1 and one is that pole 2. So pole 1 means 1 by R1 into C1, and pole 2 means 1 by R2 into C2. So we know that time constant. What is time constant? For any of RC network, the time constant is R into C. So here pole is that the fastest time constant minus 1 by fastest time constant, and pole 2 is minus 2 by second stage time constant. So R1 and R2 is nothing but the resistance ground seen from that output from first stage, and C1 and C2 is the capacitance to ground seen from output of the first stage and output of the second stage. For typical case, these poles are far away from the origin of complex frequency plane and are relatively close together. So this is that the open loop frequency response for two-stage op-amp, and this is that the open loop phase response for two-stage op-amp. This is that the first pole, this is second pole, and this one is that the angular frequency. So in this stage, that after this 0, so this one is pole 2, that will be 20 dB per decade and it is going to 0 dB frequency. So this will be from that pole 1 to pole 2, there will be the phase will be minus 45 degree per decade, it will be there, and in that the pole 2, this is that the phase margin, it will be there whenever this touches. Now is note that will be if that the feedback gain is equal to 1. This is that the worst case for stability consideration, and in that the above figure the phase margin is significantly less than 45 degree. For ideal op-amp, it should be 45 degree. But this is not ideal. We can't design any of that ideal op-amp. So it should be slightly less than 45 degree. That dotted line is 45 degree. But firm line is somewhat less than 45 degree. So this will be that the phase margin gain is significantly less than 45 degree. Which means that the op-amp should be compensated before using it in a closed loop configuration. So from that we are summarize that the phase margin for two-stage op-amp must be between 45 degree to 60 degree to get that the unity gain bandwidth product. This is that the compensation of op-amp, and this is that the procedure how we compensate any types of op-amp. Now in the next class we are going for Miller compensation of two-stage op-amp. So for that we are complete that here how to design that compensation of op-amp. So thank you.